For thousands of years, human beings have lived with natural forces like the wind and the waves. But in the last 150 years, we've learned to tap a new power that charges up our planet. We see lightning when electric currents rip the air apart. But up above our atmosphere, another, invisible current flows. It's a stream of electrically charged particles thrown out by the sun, the powerhouse for our whole solar system. The sun is a massive glowing ball of gas. It shines so brightly, you need special instruments to see the strange electric and magnetic effects here. Each one of these loops is big enough to circle our world. They're made from plasma, a boiling mix of electrons and positive ions. Magnetism pulls them into shape. It's as if a bar magnet lay just under the surface of the sun. Instead of iron filings, here the magnetic field pushes and pulls electrically charged particles. It's a clue to the mysterious link between magnets, movement, and electricity. Understanding that link has made our electric age possible and helped to explain all sorts of natural phenomena. This spacecraft does research on the sun. Its cameras stare down all day, so it must block out the direct bright light with a disk in the centre of its pictures. Each sparkle is a charged particle thrown out by a storm on the sun. This is as close as you can get to seeing an electric current. The glow is charged particles moving. Some of them brush past Earth's magnetic field as it stretches out into space. The charged particles get pulled down towards our planet's north and south magnetic poles. And when they meet the atmosphere, they make it glow. These real pictures show the Northern Lights, electricity dancing in a magnetic field. The Northern Lights are a symbol of the way electricity, magnetism, and movement are linked together. This experiment is another. The battery makes a small current that lights up a bulb, but the current also makes a magnetic field. It's just strong enough to push the needle on this compass, but only just. This battery is a lot bigger. Although it makes about the same voltage, it can send a much bigger current down this wire to work the van's starter motor. Even so, the magnetic field made by the big current is only just strong enough to push these iron filings into line. It's a small start, but the science of electromagnetism has lit up our world, and it keeps us all entertained. It's a power that can be used for good and for evil. This is a very special museum. It's used to train bomb disposal officers. Flying bombs, torpedoes, mines, underwater bombs. Many date from World War II, but they're still secret, so the museum is never open to the public. Short Circuit was given special permission to film because the story of this weapon is hardly ever told. Yet, it very nearly cost Britain the Second World War. The secret to defeating it was the magnetic field from an electric current. In November 1939, the Second World War was just 2 months old. As an island, Britain was very vulnerable. To feed the nation each week, 1 million tons of food and supplies had to arrive by ship, or the country would starve. But big ships kept sinking, cracked by underwater explosions from mines laid by the German Navy. Thousands of sailors died. Today, Chief Petty Officer Gale is one of the people who make mines from the Second World War safe.
This was Adolf Hitler's secret weapon, designed to blockade the United Kingdom and starve us into submission.
But an accident by the German Air Force changed everything. A mine that was meant for the sea dropped instead on land. Prime Minister Winston Churchill personally ordered its secret to be cracked at any cost. As daylight broke, Commander Ouvry and Chief Petty Officer Baldwin start work. They have never defused a bomb like this before. First, they unscrew the detonators, small explosive charges designed to set off the main explosion. This one was made from aluminium, a non-magnetic metal. They began to suspect that somehow the mine's secret must be linked to magnetism, and they'd found electric wires. Maybe the mine used the link between magnets, electricity, and movement in some way. For now, there was no way of knowing. Britain's future depended on finding an answer. That answer was still hidden inside a mine packed with high explosive and an unknown firing mechanism. There was nothing for it. They would have to keep looking. At last, they found a rubber disc with an aluminium dome in the middle. Under it was a complex mechanism. Complex, but as they looked closer, one word told them all they needed to know. Gauss, a unit of magnetic field strength. The mines detected big ships by the way they bent the Earth's magnetic field.
As you know, the Earth is a magnet. The Earth's magnetic field induces magnetism in the iron of a ship. And this induced magnetism causes a change in the strength of the Earth's field beneath the ship. It is this which fires a magnetic mine as a ship passes over it.
And the way that it detects the ship is through this magnetic dip needle system. This particular example does enable you to see the action of the magnetic needles. They sit in the horizontal plane. When a ship moves over the top of the mine, the magnetism activates on the needles, pushes them down, makes the trigger mechanism, and fire the mine.
To blow up the mine safely, the British Navy needed a magnetic field that would fake the effect of a big ship. So, a wooden, non-magnetic ship swept out 2 long wires called legs. They made them float with tennis balls. On the end of each wire was an electrode. Now they could send electric current through the salty sea water. The current came from huge batteries and generators on the ship. The big current created a big magnetic field, just like a big ship. Big enough to push the magnets in any mine below. Electromagnetism defeated the first of Hitler's secret weapons. It went on to entertain the nation.
The Earth is under attack. An attack from Mars!
An ordinary house in Romford is home to an extraordinary secret.
The Earth is under attack.
This garden shed is a slice through the history of electromagnetic entertainment. Dave Kingston is the pinball wizard who keeps these machines alive. The peak of pinball mania was 1975. Elton John teamed up with The Who to record a rock opera called Tommy. It built a legend around the machines that flashed and buzzed in amusement halls up and down the country. You won points when you hit targets.
Classic feature is the bumper, that's like a mushroom bumper that kicks the ball away when the ball touches it. Yeah, I mean, these are flippers that flip the ball up. As you can see, when you press the button, they flip the ball. You've got the kickers, which kick the ball about. You've got the ramps to actually achieve all the modes and bring the ball back down so it flows quite nice.
To see how the machine works, you have to look inside. It takes a whole nest of wires to feed all the flashing light bulbs, but in among them are also electromagnets. They make the game move. This one moves the flippers. And when the ball hits this bumper, it makes a contact that triggers this electromagnet to kick it out again. Electromagnets are really just coils of wire. It's easiest to see how one works away from the machine. Put a steel plunger inside the coil, then pass a current through the coil and the plunger gets pulled in magnetically. It takes very little current to do this because the hundreds of turns of wire magnify the magnetic effect strongly. The magnetic field from one turn of wire is weak, but add more turns, and now there are many wires side by side, each carrying the same current in the same direction. So there's many times the magnetic field. The more turns, the stronger the field. But electromagnets can do more than just push and pull. This cannon is moved by a mechanism of gears and levers, driven by a small electric motor. It's easiest to see the motor working when it's pulled away from the rest of the mechanism. Inside, it's clear there's a coil of wire. Here's how it works. Built into the case of the motor is a magnet. Right in the middle is the coil of wire. It's free to rotate. And through these sliding contacts, it's connected to a battery. Current from the battery turns the coil into an electromagnet. The electromagnet's south pole is attracted towards the north pole of the magnet in the motor casing. So the coil turns round to bring them closer together. If nothing else happened, that would be the end of the story. The coil would just sit still, not going round. But just at the right moment, the sliding contacts flip the direction of the current, so the magnetic field in the coil flips too. Now the coil's south pole is next to the south pole of the motor. Similar poles repel each other, so the coil is pushed away and it keeps on turning. Half a turn later, the contacts flip the current again, so the cycle repeats. The coil never quite gets to where it wants to be, and it will keep on spinning until the battery runs out. This picture shows Earth from space. Half day, half night. Every light on the right is a village, town or city lit up by electric power. In little more than 100 years, it spread right round the world. Well, almost. Colombo, Sri Lanka. The country is developing fast and the big towns all have electricity. But some remote villages don't. It would cost too much to build power lines carrying electricity here. When the sun goes down, almost everything stops. That's why villagers have started to build their own small power stations. This one's changed the lives of 50 people, giving them radio, TV and electric light. But just down the road, Gunadasa lives in a village that's still dark at night. He knew the secret to making electricity is magnetism and movement, so the village did some experiments. The children have connected this coil of wire to a meter. When a magnet moves in or out of the coil, a tiny current starts flowing. electricity is induced. But it's a tiny current, and it stops as soon as the magnet stops moving. They found that a coil with more turns made more current. Moving the magnet faster helps too. The direction of the current depends on the direction of the movement. As the magnet goes inside the coil, the current flows one way. When the magnet comes out of the coil, the current flows the other way. The current flows in alternate directions, so it's called alternating current. It turns out that it doesn't matter if it's the magnet that moves or the coil. In practice, most generators make electricity by moving the coil, not the magnet. To keep that movement going, they need a source of power, and Sri Lanka has plenty of water.
We decided to start by building a waterfall, so we brought together a group of people and went to have a look at our stream. It looked good. We reckoned it could work.
Their lives would be lit up by water power. They built a tank high above the village to collect rain, with pipes to bring it rushing downhill. Now all they needed was a generator and an expert to make it work. Lionel is an electrician who's helped many villages to generate their own power. He fixed them up with a turbine, a kind of high-tech water wheel. When water from the tank hits these blades, it will turn the generator very fast. The generator works by spinning a coil inside a powerful magnet. The coil spins round because it's attached to the water turbine. The spinning coil cuts through the magnetic field. That's what induces a current. And so long as it keeps turning, electricity will keep coming out through sliding contacts on the end of the coil. That's the theory, but would it work? There was plenty of water. And with a fresh coat of paint, the generator was ready. They just had to turn on the taps. Everything worked. The village lit up. Another corner of the world lights up for the very first time.
We've always had oil lamps, but a light bulb brings out the brightness in a home. Now we can watch TV, listen to the radio, and we don't need batteries.
Electromagnetism has changed all our lives.